Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. In networking, scope refers to the size, structure, and geographic reach of a network. Classifying networks by scope helps define how they function, what equipment they use, and what challenges they present. Scope determines everything from transmission speed to physical layout, and from media choice to maintenance complexity. These classifications, local area network, metropolitan area network, and wide area network, allow IT professionals to set performance expectations, choose appropriate technologies, and tailor their design to specific geographic and organizational needs. Understanding network scope is more than academic, it's a practical necessity. For Network Plus candidates, scope classifications appear throughout the exam in questions that test protocol relevance, device placement, troubleshooting logic, and media selection. Knowing the distinctions between LAN, MAN, and WAN helps with interpreting diagrams, matching terminology to real-world configurations, and making informed decisions during network planning and expansion. These definitions are woven into the exam objectives and are critical for passing the certification and succeeding in the field. A local area network, or LAN, is the smallest and most common type of network scope. It typically covers a single building, office, or home. LANs are privately managed and consist of devices connected over high-speed links, usually using Ethernet cabling or wireless access points. Within this confined space, data transmission is rapid and tightly controlled. LANs enable resource sharing, file access, and communication between computers and devices with minimal delay and relatively simple infrastructure requirements. Most LANs include a few key components: switches to manage device connectivity, access points to support wireless users, and cabling that links endpoints to the core of the network. LANs also use private IP addressing, such as the ranges defined in RFC 1918. These IP addresses are not routable over the Internet, which means they remain isolated from the broader network world unless a router or firewall is specifically configured to provide outbound access. This localized addressing supports privacy and network segmentation. Metropolitan Area Networks, or MANs, represent the middle ground between LANs and WANs. MANs connect multiple LANs across a broader geographic area, often spanning a campus, business park, or entire city. MANs are commonly used by universities, municipal governments, and large organizations with several buildings or sites within a single urban region. They may be owned by the organization or leased through service providers, and they usually feature higher-end equipment and specialized link types. MANs often rely on technologies such as fiber optic cabling or dedicated leased lines to connect sites. Because MANs span multiple locations, they often require regional service provider cooperation, especially when physical distance or zoning restrictions prevent direct cabling. While they don't usually span continents like WANs, MANs must deal with routing, security, and management issues that go beyond simple LAN administration. Bandwidth availability and latency are generally moderate and depend on the quality of service agreements with providers. Wide area networks, or WANs, cover the largest scope in networking. WANs connect users and systems across cities, countries, or even continents. They rely on public infrastructure, long-distance leased lines, and satellite or broadband technologies to link remote offices, data centers, and mobile users. Because of their scale, WANs must account for latency, variable link reliability, and regulatory differences across regions. WANs also require extensive planning to ensure data integrity and uptime across all locations. The differences between WANs and LANs are significant. LANs are fast and consistent, offering low latency communication and high bandwidth with limited variation. WANs, on the other hand, must cope with slower links, unpredictable latency, and greater exposure to external threats. Ownership also differs. LANs are typically owned and controlled entirely by the organization, while WANs often involve public carriers, third-party providers, and shared infrastructure. This impacts everything from pricing models to maintenance procedures. WAN technologies include a wide range of options depending on budget, location, and performance requirements. Multi-protocol label switching, MPLS, is common in enterprise environments for predictable routing and traffic prioritization. Leased lines provide point-to-point communication with high reliability. Satellite links extend connectivity to remote areas but suffer from higher latency. Broadband connections such as DSL and cable offer affordable but less controllable WAN access. Virtual private networks, VPNs, enable secure connections across public networks, effectively turning the Internet into a WAN link. When considering WANs, it's important to distinguish between private and public transport. Private WAN links such as leased lines or MPLS circuits offer consistent performance and greater control, but they come at a higher cost. Public links such as broadband or cellular are less expensive but introduce security and quality concerns. VPNs and encryption are often used to protect data over public WANs. The type of transport selected impacts network architecture, latency, throughput, and the complexity of endpoint configuration. Network scope also plays a major role in troubleshooting. In LANs, where conditions are relatively predictable and traffic is confined, troubleshooting is straightforward. Administrators often have full control over devices and media, and problems can be resolved quickly. In WANs, troubleshooting becomes more complex due to longer paths, third-party involvement, and diverse equipment. Diagnosing issues may involve coordination with service providers, deeper analysis of routing behavior, and tools designed to track traffic across multiple administrative domains. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. The scope of a network not only influences physical design, but also dictates protocol behavior. Certain protocols are designed to operate only within local environments and may not function correctly or securely when extended across wider scopes. For example, protocols like NetBIOS and certain file-sharing services are limited to LANs due to their broadcast-based discovery mechanisms. In contrast, protocols like Border Gateway Protocol, BGP, Simple Mail Transfer Protocol, MSPP, and Virtual Private Networks, VPNs, are purpose-built for WAN environments, supporting communication across extended paths with multiple routing points. TTL, or time-to-live values, in IP headers are another example of how network scope affects protocol behavior. A short TTL may work fine within a LAN or MAN, but on a WAN it might expire before reaching the destination due to the number of hops. Similarly, fragmentation is more likely to occur in WAN environments, especially when packets traverse different providers' infrastructure with varying MTU sizes. Understanding how these behaviors shift across scopes ensures proper protocol selection and network tuning. Bandwidth and performance characteristics also vary dramatically by scope. In a typical LAN, connections are fast and stable, often reaching gigabit or even multi-gigabit speeds with minimal latency. A MAN, depending on the provider and underlying technology, offers moderate speeds with potentially increased latency due to distance and infrastructure sharing. RAN links tend to have the slowest speeds and highest latency, especially when relying on satellite, cellular, or congested broadband networks. Performance planning must therefore account for distance, path variability, and the limits of available technologies. Cost increases significantly as network scope expands. Building and managing a LAN is relatively low cost, particularly in environments that already have cabling and infrastructure in place. MANs require coordination with service providers, often involve recurring fees, and may need custom fiber deployments or leased lines. WANs are the most expensive to build and maintain, involving long-haul data transport, international coordination, and complex service-level agreements. These costs include both capital expenditures and ongoing operational fees, which must be factored into any large-scale networking project. Design priorities differ depending on whether you're dealing with a LAN, MAN, or WAN. In a LAN, the focus is often on maximizing speed, minimizing complexity, and supporting a high density of devices. Simplicity is key and performance is generally high. A MAN balances the need for extended coverage with a desire to retain administrative control. Fiber connectivity between campuses or office buildings must be reliable but not overly complex. WAN design, however, centers on reliability, failover capabilities, and security. It must account for unpredictable links, provider handoffs, and traffic optimization across potentially global paths. Typical use cases highlight how these scopes function in real-world settings. LANs are used in homes, small businesses, and single-office buildings to connect workstations, printers, and local servers. MANs are commonly found in universities, city governments, or enterprise campuses that span a defined geographic area. WANs are used by multinational corporations, financial institutions, and large service providers to interconnect branch offices, cloud services, and global customer access points. The purpose of each scope drives the infrastructure and protocol decisions needed to support those objectives. Different devices are prioritized based on scope. In a LAN, switches and routers handle the bulk of traffic management, with access points extending wireless coverage. In a MAN, aggregation switches and regional routers connect multiple LANs and may tie into fiber rings or leased lines. WANs require more advanced infrastructure, including edge routers, modems, and sometimes satellite terminals or cellular gateways. Each device plays a specific role in managing flow, securing connections, and ensuring stable performance, appropriate to the scope in which it operates. Network addressing also shifts as scope expands. Within a LAN, private IP addressing is the norm, with devices assigned from reserved ranges. These addresses are non-routable over the internet and are translated at the edge using network address translation, NAT. MANs may still use private addressing, but often require more advanced routing policies to manage overlapping networks. WANs frequently require public IP addressing for routability and compliance with service provider infrastructure. Addressing policies, including static versus dynamic allocation and subnetting, become more complex as the network grows. On the Network Plus exam, scope definitions may be referenced in questions involving diagrams, performance descriptions, or design recommendations. You might be asked to identify whether a given setup is a LAN, MAN, or WAN based on the scale and components shown. Other questions may describe symptoms such as high latency or public IP usage and require you to determine which scope is being referenced. Understanding the distinctions helps you make accurate judgments and connect terminology with topology, media, and protocol behaviors. LAN, MAN, and WAN definitions provide the framework for understanding network reach and capability. These classifications shape the technology choices, hardware requirements, cost structure, and design strategies used across environments. Mastering their distinctions supports effective planning, sharpens troubleshooting skills, and prepares you for certification success. Whether designing a small business network or deploying a global infrastructure, the foundational knowledge of network scope ensures that your architecture is fit for purpose, resilient, and scalable. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.